In our lectures on structural systems reliability, so far we have looked at the series configuration, whether it be a non-redundant structure which would fail if any one of its members fail, or it be a structure with multiple failure modes and the structure fails if any of those modes occur, or a situation of dual or multiple performance levels or multiple load combinations. And in each of these situations, we ended up with a series configuration. In this last lecture on systems reliability, we are going to look at parallel and other active load sharing redundant systems. Let's see what interesting feature this sort of systems have. So what you see on the left is an active parallel system. Again, the simplest possible situation where we have two members loaded by a common load P, and the load is shared by two, not necessarily equally. In this particular situation, for equilibrium, we have P balanced by alpha P in the left member and 1 minus alpha P in the right member, as long as both members are intact. Now, this system itself, we understand that if one of these two members fail, it does not fail automatically, provided the remaining member, the surviving member, is able to pick up the slack. So we have a redundant system in hand, and in this particular example, this is an active parallel system. So let's see what are the issues of such a redundant system. So let's walk through the flowchart on the right. So we have discussed that a structure may fail under overload or under cumulative damage. So let's see what the overload would do to the failure of a redundant structural system. So if there is suddenly a huge, massive load on part of a structure, then one or more major members or subsystems can fail, and almost simultaneously without any chance of warning or redistribution. And while that happens, it's possible that there could be dynamic amplification, there could be load reversals and such in the surviving members. And if it is not possible to reach a stable configuration after this massive damage with load redistribution among the surviving members, then we would have global failure. On the other branch, we could have, for the redundant system, a local failure. This local failure could involve one member, two members, due to cumulative damage. For example, a member may have increasing corrosion or increasing crack size, and then finally it's not able to take that load under normal operating loads, and there is that local failure. Then, due to this failure, we could have, just like in the earlier case, in the left branch, there could be dynamic amplification, there could be load reversal in some of the nearby members. And then these members would experience higher loads, and which might or might not be arrested. So if it's not arrested, then a chain of failure occurs, and again to a point that we cannot have a stable configuration formed, and leading to global failure. So a series system does not have this complication or luxury, if I may use the word. Any member failure, any single logical element failure means the entire system has failed. But if we have a redundant system which may be able to absorb partial damage and not fail, would undergo a more complicated set of events leading to global failure. And if we need to analyze the system reliability for such a redundant system, then it is clear, would need to analyze the structure both in intact state as well as in damaged state. For example, looking at the simple two-member active parallel system on the left, we know by inspection that in intact condition, the loads in the two members have to balance the applied load because of static equilibrium. And if one of them fails, then the other one has to pick up the slack. Now, I'm using this word pick up the slack deliberately because it is not necessary that if one member fails, it will not be able to carry any load at all. And this is one of the peculiarities of a structural system, that failure does not mean complete loss of load carrying capacity. The material may behave in a manner that some residual load carrying capacity may still remain after the member fails in some sense. So even for this very simple system, we see that once partial failure occurs, once a member fails, it is not completely straightforward what happens. We have to take into account how the remaining, how the surviving structure behaves, and that in turn needs to take into account what sort of material behavior the members have. So we are going to look at this in the next few slides. We are going to look at two extreme cases, two ideal cases. On one end, we have complete brittle behavior, which means as soon as the failure load is reached, the member completely fails and it is not able to provide any resistance. On the other end of the spectrum, the material can be ductile and it flows perfectly, and at failure, it is still able to provide some remaining resistance equal to its failure load, and that's why I said the other member needs to pick up the slack. So let's work through these and see, even for this very simple two-member active parallel system, what sort of insights we can get.